All right, welcome back. This will be the first lecture after the test. We've already done relativity, special relativity specifically, and now we're going to look at the photoelectric effect. Now, just a little background. We have the nature of light as per the double slit experiment of Thomas Young. We know that light must behave as a wave. From Young's double slit. Now, you see here, the title says the particle nature of light. So you can see we're going to have a little bit of a conflict here. So let's talk a little bit about Einstein before we get started. Albert Einstein, in my mind, a lot like Isaac Newton. Albert Einstein wasn't the dedicated student that we always tell people they should be. He went to school, went to college. He didn't do as well in college as he could have because you know how the teachers have the pesky lectures and stuff that's just boring? Well, he didn't dig that. So, for instance, you might have heard quotes about Einstein and math and how he has problems with math. Well, Einstein didn't like going to math class, so he didn't. But of course, he had to pass class. So the night before tests, he would get together with a buddy who became a preeminent mathematician. And he'd say, okay, so what do I need to know for this test? And then he would go in and he would pass his tests. That's pretty brilliant to not study, not go to class, and just cram the night before and pass his classes. So he was a brilliant man. But he didn't really fit into academia as a youngster. So when he graduated from college, he got that job working at the patent office. And he considered that the best job he ever had in his life. Because every day he got to look at people's amazing ideas and evaluate, hey, will this work or is this, a bunch of garbage? And then the evenings, he and his friends would get together at the local pub and have themselves a root beer and talk about the latest scientific papers and mock people who made mistakes and, just living the life. But then in 1905, his entire world changed. In 1905, Einstein wrote 3 papers. One paper was on the photoelectric effect. One paper on a theory of special relativity. And one on explaining Brownian motion. And I think I mentioned this before when I was introducing relativity, but these were amazing world-changing papers. And the one that he actually got a Nobel Prize for was the one on the photoelectric effect, the one we're going to be studying today. So let's get into it. Now, we have to start by understanding quantization. Quantization means that we break things up into packets or quanta. And so energy is an example of something that we quantize. You only have certain energies. And the way I often like to talk about this is imagine you have a staircase and you drop a bag, and that bag could be on any of the stairs, but the bag can't be hanging out somewhere between the stairs. It's only going to have certain elevations or energy levels, since potential energy, gravitational potential energy, is mgh. So you drop a bag of groceries on the stairs and you have quantized energy levels for that bag of groceries. It's only going to be on one of those stairs. That's what it means for something to be quantized. We've already seen some examples of things that are quantized. When we studied music, you pluck a string on a musical instrument and you only hear, a frequency or integer multiples of that frequency. It has quantized frequencies. There's only certain frequencies that will resonate on that string. So the frequencies that resonate, f sub n is equal to n, which n could just be any integer, a positive integer, multiplied by the fundamental frequency. And so you might remember looking at exactly this graph when we were talking about why it was quantized, because you had the condition of a node because the string was fixed on both sides. So it had a node on each end. And you could have a node on each end if you have 1/2 wavelength is equal to the length, or here it's a full wavelength is equal to the length, or here it's 3/2 wavelength is equal to the length. And so you get the relationship between length and the wavelengths that can resonate. And that's how we set up the quantization there with the waves on a string. Now, just to make sure you got this, what does it mean if a quantity is quantized? When we talk about quantum physics, people often just say, oh, small. That is not what quantized means. Quantum physics is often called the physics of the small, because in small things is the only case where we really see a difference in quantum physics calculations compared to classical physics. But it doesn't just apply to small, or it isn't exclusive to small. Okay, so the second object, the object associated with a quantity that is very small? No. The quantity can only have positive values? Well, that's not true. It can only have negative values? Nope. Discrete, there we have it. It can only have specific values. It can't have any old value. That's what it means to be quantized. So how did this whole blackbody thing come about? It starts with blackbody radiation. Blackbody radiation, the reason we say black here is because black is the ideal color for something to radiate. If something is black, it's a perfect emitter of radiation. And we know about blackbody radiation just because a normal incandescent light bulb, we have a piece of wire and we make that wire hot and it gives off light. That's what blackbody radiation is. So we call that incandescence in the light bulb. And so, of course, physicists were trying to understand, why is it giving off light? And we had people like Wien, who came up with this displacement law that said that there was a relationship between the peak wavelength. So if you plot intensity of blackbody emission as a function of wavelength, so here, this one here has wavelength, then you're going to have the wavelength that's at the peak is equal to 2.897, I'm just going to truncate it here, 8 times 10 to the 6th nanometers times kelvins divided by the temperature. So as the temperature goes up, then the wavelength of the peak is going to get shorter. And so on this frequency one, of course, frequency, remember, frequency is equal to the speed of light divided by wavelength. So if you raise the temperature, if the wavelength for the peak is going to get shorter, then the frequency for the peak is going to go up. So this shows you the peak moving up at different temperatures in frequency, which would be down in wavelength. So if you have something like an incandescent light bulbs are actually somewhere around this temperature. So most of their radiation, in fact, 95% of their radiation is infrared. It is frequencies below red. So here's, of course, red. So this region here is infrared. So incandescent light bulbs, only 5% of your energy is going into light. And that light has more red, less blue. So it's not really white. It's kind of a reddish color. And if we were in class, I would do some demonstrations to show you this. So this is Wien's law right here. Very simple. Tells you about the peak for radiation as a function of temperature. But then also, they tried to come up with equations to give us the shape of that radiation, that emission curve. Now remember, this is the intensity on the vertical axis, and the left one, it's frequency on the horizontal. The right one, it's wavelength on the horizontal. And so in trying to come up with that, Lord Rayleigh and I don't remember what Jean's first name was. And of course, Rayleigh, Lord isn't his first name, that's his title. They, I think independently, came up with an equation that was absolutely perfect by classical physics to describe what the shape should be. And it fit very well at low frequencies or long wavelengths. But it diverged grandly as you got into short wavelengths or high frequencies. And so what their theory actually said was the amount of emission you have at high frequencies like ultraviolet is approaching infinity regardless of the temperature. So basically, if you think about that, you're giving off an infinite amount of energy no matter what the temperature is. That doesn't fit with conservation of energy at all. And so they had a catastrophe in theory. And so it's called the ultraviolet catastrophe because they know this can't be right. It violates our laws of physics. And so scientists were madly trying to figure out what in the world is going on. Why is it not the way it seems it should be? Well, let's go to October 17, 1900. Max Planck was told by Heinrich Rubens that Wien's law broke down at low frequencies. So this equation we saw here, that equation at low frequencies, it broke down. It didn't quite work the same. And it was based on, how it varied with temperature. And so Wien sat down that night and he said, well, if that's the case, then we should have a relationship that says the intensity as a function of temperature has, and he came up with his own equation. So he came up with an equation, he sent it out that night, and lo and behold, it was correct. It gave exactly the right shape for the observed blackbody radiation. So Planck had a major discovery. Only thing is, he didn't have a reason for it. His only reason was based on the way the emission behaves at low temperatures, this equation should give us the shape. So it was a fit, but it wasn't a theoretical reasoning. And as a physicist, what's a physicist trying to do? Trying to understand how nature works. So having it does this, but not the why, is really disappointing. So Planck sat down and worked his little hiney off trying to figure out what physics could make this happen. And in December of 1900, he proposed a revolutionary idea. He said, if light comes in little packets of energy, and those little packets of energy have an energy of some constant times the frequency. So I could have one constant, one packet, two packets, three packets, but I couldn't have any amount of energy at a given frequency. Then he could actually come up with a physics explanation to give his equation. So this is a quantum hypothesis, Planck's quantum hypothesis. He said, if light were to do this, then I could give you a physics explanation for why my equation is correct. Well, that's not quite all the way there. Here's just some clarifications about that equation. So E0 is the energy for a quanta of light. And that quanta of light we call the photon. Photo for light, on just for something, say, hey, it's a particle. So the energy for a photon is Planck's constant, h, multiplied by the frequency in hertz. And here is the new and improved value for Planck's constant, 6.626 times 10 to the minus 34 joules times seconds. So if I have light of, let's say, let's just take something really simple. We have people these days who are proposing that 5G communications for your cell phone is somehow causing the coronavirus. And so what is the frequency for 5G? Frequency for 5G is somewhere between, let's just go with the highest value it has. So 50 or 86 gigahertz is the highest frequency used for the 5G radiation. So that's 86 times 10 to the 9 hertz. And so if we want to calculate the energy for the quanta of light, the photon, we'd have energy for a single photon of this is equal to 6.626 times 10 to the minus 34 joules times seconds multiplied by 86 times 10 to the 9th hertz. And I actually have to type that in to get the answer. That's 86 into 9. And so that is an energy of 5.698 times 10 to the minus 23 joules. Now, for energies that small, we usually put them in electron volts. So I'm going to multiply that by 1.609 times, or divided by, excuse me. Times 10 to the minus 19 coulombs per electron. And so take that divided by I, of course, didn't do it in the right place. Well, God bless me. I apparently can't do math right. Well, it gives us an energy that is, and I'll try it again. I'm just going to round off the 5.7 divided by 1.6. 2319 is 4. So that's 3.6 roughly times 10 to the minus 4 electron volts. Remember, electron volt is the charge of an electron times a joule per coulomb. That's the energy of a photon of that 5G radiation, the highest energy it gets. And people are concerned about this causing damage to us. Well, you know what? That's a small energy for a photon. And on average, each photon is going to be absorbed separately. And so the most that any single bond in a molecule in your body would absorb is that much energy. Well, the light that we are always bathing ourselves in has energy, has frequencies in the range of 10 to the 14th hertz, or 4 times the frequency of 5G, which means its energy is on the order of an electron volt. So this is far, far less energy per particle of light from 5G than you have from visible light. And so the damage potential of 5G radiation is orders of magnitude lower than the damage potential of visible light. It really isn't something to be concerned about. Now, before I finish with my little conspiracy theories, let us keep in mind that we can cook food with a microwave oven. A microwave oven is using frequencies that are, low frequencies such as we use with cell phones. And so it's a low energy per photon there. And you might ask, well, how do we cook it then? Well, what we're doing is we're putting in a lot of energy. So there's small amount of energy absorbed by each bond, but the total amount of energy is large. So you put in energy, it heats up and it cooks. So there is always the concern, maybe you're going to cook yourself with your cell phone radiation. And I didn't come prepared to do any calculations on that, as I don't know what the power output is, for instance, of a cell phone. But generally speaking, you're not putting in enough to cause any damage. Now, Heinrich Hertz set about in 1886 and 1887 to test James Clerk Maxwell's theory that light was an electromagnetic wave. So he used a spark gap generator to create electromagnetic waves. And he has in his margins that when he polished the surfaces, they worked much better at emitting or at arcing. And he didn't know what it was at that time, but that was the first discovery of what Einstein's photoelectric effect is. So let's jump now to Einstein, now that we've spent half of our class period. So in 1905, he explained the photoelectric effect. That is, so let's describe the photoelectric effect. The photoelectric effect is light hits a surface and an electron comes off. That's the entire effect. Light in, electron out. We call these electrons out, quote, photoelectrons. Can't spell electron today. There's no difference between a photoelectron and any other electron, but we call them photoelectrons because they were emitted from a surface because of light. So Einstein said, okay, this photoelectric effect, this effect of electrons coming out of an object because of the light in, is going to be affected by the particle nature of light. And he predicted results of experiments that hadn't been performed. That's the way the scientific method is supposed to work, right? You observe something interesting. Hey, we got this photoelectric effect. Hey, we've got this theory that light's a particle. You make a hypothesis because the light is a particle, then the energy of one photon, which is equal to HF, is absorbed by one electron. And so that electron comes out with a kinetic energy that's less than or equal to the energy of the photon. Now you might say, hey, wait, why less than or equal to? Well, the electron absorbed the energy of the photon. So the electron started with HF, but it might have bounced around from some things and lost some energy. Furthermore, there's actually energy required to remove an electron from the surface. We call it the work function. If it was free, electrons would just leave the surface when they got to the surface. So there's a certain energy loss. So that's why it's less than or equal. In fact, it's just less than because of the energy lost required to break it away. So what he said is, this means that the photons coming off, if the photon absorbs that quanta of energy, or excuse me, the electrons coming off, if they absorb that quanta of energy of the photon, then they're going to have a maximum kinetic energy. So doing the math, and I'm sure I have it somewhere, but I'm just going to write it here. The kinetic energy maximum of a photon coming off, or a photoelectron coming off, is equal to the energy of the photon, HF, minus what we call the work function of the metal. So that's his equation. The kinetic energy maximum that you get for electrons coming off, so they'll be going anywhere from there to zero, is the energy of the photon minus the energy of the work function, the energy required to remove an electron from the surface. So here's the apparatus like we would have used in lab next week. You have a photocell that has a metal plate that you're going to shine light on, and then it has a collecting wire here. And so when you shine light on that metal plate, electrons come off. And those electrons will come over and be attracted to this collecting wire until the voltage, well, as soon as an electron leaves that metal plate, it's going to become negative in charge, or positive in charge because it lost an electron. And if this one here absorbs an electron, it will become negative. And so you start to build up a difference in voltage, and the electrons will continue to move from this plate to that wire until you reach the point where the kinetic energy of the electron coming off is equal to the energy required to go between those. So the energy required to go between those is Q, the charge of the electron, times the voltage difference between the metal plate and the collecting wire. And that's going to be equal to kinetic energy max when it stops building up voltage. which is HF, minus the work function. And so we have a relationship here that says the charge of an electron, I can replace Q with E because we know the charge of an electron, E. And so we generally just divide everything by the charge of an electron, and we have the voltage difference between the plate and the collecting wire is equal to HF over E minus the work function over E. So this is what in lab we were going to do, and we'll probably do a simulation. We measure the voltage as a function of frequency, and we make a graph. And we find the slope. And according to this, if I have voltage on this axis and frequency on this axis, then the slope is H over E. And the y-intercept is minus the work function over E. And so we can calculate, based on using different frequencies and making a graph, what Planck's constant is and what the work function is for our piece of metal. Now, going back to Einstein. Einstein said, this experiment will prove, of course we can't prove anything in science, but it will give us a disproof of the wave theory. Because wave theory says that, I have the experimental results here. I should talk about that before I go there. Wave theory would say the energy of an electron is proportional to the intensity of the light. You make the light brighter, you have more energy per unit area, hence more energy that the electron can absorb. And if you change the color, no difference. Because it's just the intensity that matters. Whereas if you go with the particle theory, that's Einstein's, the energy of the electron is proportional to the frequency. That's the color. So color matters. And intensity will affect number of electrons per second emitted. So if you have more intense light, you're going to get more electrons per second emitted, but they're going to have the same energy. So we have a clear distinction. Wave theory, you make it brighter, you have more energetic photoelectrons, and color doesn't make any difference. Particle theory, you make it brighter, you get more electrons per second, but the energy doesn't matter. Change the color and the energy changes. Clear, distinct differences. So the experimental results, brighter light causes an increase in current, that is more electrons are ejected per second, but doesn't change the energy. So that is a clear, definitive, it's not behaving like a wave would, it's behaving like a particle would. So Einstein's, there's a second one here. When you make the graph, you get a graph like I showed you. Now notice this here has minus phi. Phi is just the work function divided by the charge of an electron. So it's the work function in volts. It's just easier to do it that way. In electron volts, okay. So the experimental results, they exactly match Einstein's theory. And so we had everybody in the world believing light is a wave because of Young's experiment. And now we have Einstein with an experiment that proves light's not a wave. And so, what is physics going to do? It's thrown into a tizzy. One more thing, I forgot that I had this here. There is a threshold frequency for, if you look at this graph, threshold frequency is right here. There's a minimum frequency to have enough energy to escape. And so remember, we had the delta V is equal to HF minus HF over E minus the work function over E. That's the way I wrote it before. So using the notation here, if I solve for frequency, I have frequency is equal to, actually, I don't even need to solve for frequency. All I need to do is say, if my delta V equals 0, that is, if I have a cutoff here, right, here's the delta V right there, then I'm going to have we put a subscript 0. And so the work function in joules over Planck's constant gives us that cutoff frequency. So that's the minimum frequency we're able to emit electrons. Oh boy, there was a fourth one. Yeah, that's not an important one to me. Now, just question, make sure we're paying attention. Who came up with the idea of light being quantized? I knocked myself out and put full names of people. Wilhelm Karl Werner Otto Fritz Franz Wien? Or Hermann von Helmholtz? Or Max Karl Ernst Ludwig Planck? Or Albert Einstein? Or William John Strutt, the third Baron, I said Lord, Rayleigh? Or Robert John Strutt, the fourth Baron Rayleigh? They were both physicists. Well, the answers, let's just make sure we remember, he came up with Wien's law. Wilhelm Wien came up with Wien's law, which explained or gave an equation for the peak wavelength of emission based on temperature of a black body. Hermann von Helmholtz did a lot of good physics, as did Lord Rayleigh. Albert Einstein took the quantized idea and ran with it. But Max Planck was the person who originated the idea that he could explain the blackbody radiation shape, intensity versus wavelength, if light was quantized. Well, that is a short lecture, but that is our lecture on photoelectric effect. Have yourself a great day.